Ciao! Welcome to this new episode of the series related to probability and stochastic processes. In this episode, we will investigate two fundamental theorems about probability, which are the law of large numbers and the central limit theorem. So let's start by investigating the law of large numbers. So in order to do this, we can start in a heuristic way. So let's start by considering a regular dice, so that in every phase we have a different number between 1 and 6. So this is equivalent to say that we have a fair dice with the equal probability to obtain one of the number between 1 and 6. So in general, this dice is so that the outcome a priori is a random variable. Let's call this as x1. Okay, so this is of course an a priori random variable, since we do not know the outcome of the dice. So in general, we expect it to be between 1 and 6, but in general we don't know which will be the outcome. So in this sense, we say that this is a priori a random variable. Okay. So in general, let's assume to roll this dice, we will obtain a certain outcome for the throw. But after the first outcome, we can try in general to roll the same dice again, in general n times. So we can define more random variables, starting from x2, which corresponds to the second rolling of the dice, up to xn, which corresponds of course to the nth rolling of the dice. So we have in general a subset of n random variables starting from x1 to xn. And all these random variables are of course independent and also identically distributed. They are independent since a certain throw of the dice we will not influence in any way the roll, another roll of the same dice. This is equivalent to consider n different dices. Okay, so throwing the same dice n times or throwing n dices one time is the same thing with respect to the definition of the random variable. And they are identically distributed since in every single rolling of the dice we have the same probability mass function. Okay, so we will give now a very short definition of what is meant to be what is the probability mass function, but we will investigate further this concept in the next videos. So let's assume to fix, as always, two Cartesian axes, and let's try to figure out what this probability mass function means. So let's start by putting into the x-axis all the possible outcomes of the dice, so all the integer numbers between 1 and 6. So we define in general the x-axis only with the letter x, okay, while we define the y-axis as f of xy of x. Okay, so xi here means that we are considering one generic random variables among the n random variables that we have generated through rolling the dice, the rolling of the dice process. Okay, so but we are interested in understanding what this f stands for. Okay, so let's try to figure out this concept trying to draw something. Okay, so let's assume to put 1/6 over here, over the y-axis, okay, because if the dice is regular, so if the dice is fair, we expect to have the same chance to obtain 1, 2, 3, 4, 5, or 6. So all the faces of the dice are equal in probability terms. So we have the same probability to obtain one of these numbers. So fxi of x is called probability mass function. And this is a function which associates to every possible outcome a probability. So in this case, we can say that the probability mass function is defined as the probability for xi to be equal to x, of course. In general, we can compute, of course, the expectation for a generic of these n random variables, which we can indicate with the Greek letter mu. So mu I, which is the average value for the yth random variable xi, is equal to this sum. So this sum means that we are summing all over the possible number of outcomes, so in this case from j equal to 1 up to 6, of the possible outcome, okay, times the probability mass function evaluated into this xj, okay? And since they are all the faces of the dice are with equal probability, we will have basically 1 times 1 over 6 plus 2 times 1 over 6 and so on until 6 times 1 over 6. And this is equal to 3.5, which is here reported. Okay, and here we can extend this result to all the random variables we are considering, since they are independent and also identically distributed. So we can in general indicate with a single Greek letter mu the mean of the population, basically. So mu is equal to mu1 equal to mu2 up to mu n. So they have all the same average. So let's try to make another step forward into the definition of the law of large numbers. So have always in mind that all the random variables xi which are considering are independent and identically distributed. So we can now construct a new random variable which is capital N Sn, which is simply defined as the average sum of all the random variables that we have generated through the experiment. So we can construct now and compute the two most important statistically relevant quantities, which are the mean and the variance. For the mean, we can simply apply the expectation to this new defined quantity, and through the application of the linear property of the expectation, we can isolate this 1 over n term, and so we can transform the expectation of the capital Sn into 1 over n times the sum of the expectations for every single random variables. And since they are all identically distributed, we can just obtain mu. The same principle holds also for the variance, and by applying the definition and through the fact that they are independent and identically distributed, of course, we can simply obtain sigma squared over n, where I assume here that every x1, x2 and up to xn, each one of these random variables has a variance which is equal to sigma squared. Okay, so this is the variance for the single random variable. So let's move on into the formal definition of the law of large numbers. And for the future, if I will remember, my intention will be to express a theorem like this. So the term theorem followed by the name of the theorem itself. Okay, So formally, the law of large numbers says that if we consider x1, x2 up to xn like random variables in such way that they are IID, so we are considering n independent and identically distributed random variables. If we now construct the new random variable which is obtained as nothing but the average sum of all the previous introduced IID random variables, then Sn converges in probability to the mean of the population mu. And we indicate this through this notation. So Sn, okay, Sn converges in probability, we indicate by fixing a p over this arrow. So Sn is converging, which is the arrow, in probability terms to mu. Okay, do not expect now to understand the difference between the types of converging properties of the random variables. We will investigate those properties further in the next videos, but this simply says that if we take a potentially infinite sample, so if we let n to go to infinity, so this means that n goes to infinity. Okay, so this is written very bad, but I think that the concept is clear. So if we are letting n to grow up to infinity, we will see that the probability for Sn to be equal to mu is 100%, so is equal to 1. So we can say something like this: the probability for Sn to be equal to mu is equal to 1 if limit, okay, I am writing with my mouse, so this is very bad, I'm sorry for that, but I think that is clear for you. Okay, so the limit for n which goes to infinity of the probability of Sn to be equal to mu is equal to 1. Okay, so this means converges in probability. Okay, in general, if we want to be more formal, we should observe that in reality there exist two different forms of the law of large numbers. In particular, there is the weak law of the large numbers and the strong law of large numbers. But we are not interested here in understanding this difference. So for us, it's only sufficient to observe that if we let the sample to grow indefinitely up to infinity, we will have that Sn will go to mu with probability equal 1. Okay, this particular property is called as consistency. So we can say that Sn is a consistent estimator for the population mean. Okay, we will see what precisely mean for an estimator to be consistent in the properties of the estimators in the next videos. Okay, so let's move on and try now to introduce the central limit theorem. So we start basically with the same identical assumption as the law of large numbers. So we are considering, as always, all the random variables x1 to xn to be random and IID. Okay, so if we now construct the same random variable obtained as the average of the all random variables, then we can say that Sn converges this time in distribution to a normal distribution with mean equal to mu and variance equal to sigma squared over n. And remember that these two parameters, so mu and sigma squared over n, are precisely the mean and the variance for the random variable Sn just introduced. Okay, so this result, together with the law of large numbers, can be condensed. Okay, I'm sorry, I was forgetting this concept, but we indicate the convergence in distribution in this sense. So while from one side we have the law of large numbers, which gives us information about the probability of this new random variable, we have on the other hand that the central limit theorem is giving us information about distribution. Okay, so this difference is important, but in general all these two theorems are of fundamental importance, and their result is not trivial. They are a very powerful instruments in order to understand the asymptotic behavior of random variables. So let's now try to condensate all these results. Okay, let me clean this notation. So let x1, x2 till xn be random IID variables. If we now construct the new random variables, which is the average mean, okay, we have basically two results. Law of large numbers, which says that the new random variable converges in probability to the mean of the population, and the central limit theorem, which says that the random variable converges in distribution to a normal variable with mean equal to mu and variance equal to sigma squared over n. I hope that you enjoyed this lesson, and please, if being not clear in some points, please let me know into the comments, so I will try to provide you further explanation for this. And so let's see us into the next videos, where we will investigate the most common distribution function. Then we will see the estimator properties and the different types of convergence for the stochastic variables. See you into the next video. Ciao!